Okay, in this problem we're going to use implicit differentiation to verify that the two families of the curves are orthogonal, where C and K are real numbers. So orthogonal again means that the tangent lines of the curve are going to be perpendicular to each other. So let's define perpendicular a little bit differently. We have been saying that perpendicular lines have slopes that are negative reciprocals of each other. That is very true. 2/3 and negative 3/2 are negative reciprocals of each other. We can also say that when we multiply those negative reciprocals together, we get a product of -1. We will be using that knowledge to be able to verify that these two families are orthogonal. So in this first curve, I'll go ahead and find the derivative of it. And the derivative would be 2x plus 2y dy over dx equals 0. Solve for dy over dx quickly. Dy over dx ends up being negative 2x over 2y. But I'm going to simplify that, and I get negative x over y. Now I need to look at my second curve, y equals kx. Take the derivative, dy over dx equals k. Now using this knowledge, I'm going to talk about multiplying those two slopes together. And hopefully that will find out that the two slopes, when we multiply these two together, the product of those equals -1. So does it equal -1? That's what we're really asking ourselves. Well, right now it doesn't. But if I look a little bit further, I'm going to be able to replace this y. This y can be replaced with a kx. So I'm going to have negative x over kx times k equals -1. What did that now allow me to do? Well, it allows me to cross-reduce my k's. It also allows me to reduce my x's. So I do get that -1 equals -1. So I have verified that these are orthogonal. Next problem, I'm not going to have the time to talk about differentiating this with respect to x. We have done nothing but that. That's when we solve for dy over dx. What we're going to do different is we're going to solve this with respect to t. So none of these variables are t's. So every time I take the derivative of something, I'm going to have to put dx over dt or dy over dt. Those are the two variables we have in this problem. So we're going to take the derivative of this x, which would be 2x, and we're taking the derivative of x with respect to t, so I'm adding in my dx over dt. I'm going to change this to plus the opposite. Otherwise, I'm going to end up losing my negatives, and that will be a problem later. So strongly urge you to change your signs to plus the opposite, especially since we're doing a product rule. So we're going to do first times the derivative of the second. The derivative of the second is 2y. This isn't a t, so I have to write, I'm taking the derivative of y with respect to t, plus the second times the derivative of the first. The derivative of the first is -3. This wasn't a t, so I have to say I'm taking the derivative of x with respect to t. Plus the derivative of y cubed is 3y squared. It is not a t, so I have to write the derivative of y with respect to t, and then equals 0. I will not be able to solve for just dy over dt or dx over dt, so what I'm going to do is I'm going to collect my dx's over dt on one side and my dy over dt's on the other. So looking at this problem, I have really 2x dx over dt plus -6xy dy over dt plus -3y squared dx over dt plus 3y squared dy over dt equals 0. I'm going to keep these two dx over dt's on the left-hand side. 2x dx over dt minus 3y squared dx over dt equals, I'm going to move this other 2 to the right-hand side. So I'm going to have 6xy dy over dt minus 3y dy over dt. And that is as far as I'm going to be able to take it.